Engineering thermodynamics, thermal equation of a state of fluids. Fluids are used in many production processes in the industry. These fluids, whether liquids, gases, or mixtures of both of them, are stored in tanks and transported through pipes in industrial installations. The volume that each kilogram of fluid occupies in these installations may vary if pressure and temperature do so. Finding this interdependence between pressure, volume, and temperature is crucial in order to scale up tanks and pipes. The knowledge of the mathematical relation that physically demonstrates the interdependence between these three properties is essential in engineering. In this video, we will see in an experimental way the interdependence that relates pressure, volume, and temperature in fluids. A practical case will serve as guiding thread. In this video, we will show the mutual dependence in the state variables, PVT, for the fluid contained in a variable volume when pressure and temperature are modified. The distinction of the fluid properties in the different operating regions. The obtention of the vaporization curve, PT, as well as the PV diagram for a fluid. Description of the apparatus. We will start describing the experimental device. The laboratory device is composed by a graduated tube that contains the translucent fluid with which the experiment will be conducted. The volume of the gas contained in the tube can be controlled by moving a mercury column upwards or downwards, operating on a rotating wheel. This volume can then be measured in the graduated column. The maximum reachable value of this volume is 4 cubic centimeters. The pressure of the fluid is measured by means of a manometer located in the bracket of the device. The spin of the wheel, changing the volume, produces also a change in the pressure. The manometer is able to measure pressures up to 60 times 10 to the power of 5 pascals, that is to say, 60 bar. Due to safety reasons, we won't exceed 50 bars. The temperature of the fluid is measured indirectly. The tube that contains the fluid is surrounded by another concentric tube. The annular space is filled with water proceeding of a thermostatic bath. When a steady equilibrium between the static fluid and the water is reached, the temperatures of both fluids are the same. Then, it is only necessary to measure the temperature in the water. With this apparatus, we will measure temperatures in the range from 20 to 50 degrees Celsius. It is important for the correct realization of the practice to maintain pressure, volume, and temperature values stable in time while measurements are taken. This state, in which properties remain stable in time, is the so-called steady state. The fluid that fills the measurement tube is sulfur hexafluoride. This is an inorganic compound which its formula is SF6. In gas state, it shows a high dielectric resistance, good insulating. Due to this fluid is commonly used as insulation in electric distribution systems, especially in high voltage. Sulfur hexafluoride is also used in some industry steel processes, as well as in eye surgery. It is considered as a greenhouse gas, listed with a GWP of 23,500. Because of its large density value, sulfur hexafluoride doesn't rise the upper layer of the atmosphere. Nevertheless, due to its long atmospheric lifetime, 3,200 years, its contribution to global greenhouse effect is high. Preliminary measurements. Thermal equation of a state. The first thing we will do is to check if any interrelation between the three properties, pressure, volume, and temperature, exists. To this purpose, we will handle and change all the control elements of the apparatus, as well as the thermostatic bath and the rotating wheel, and see what happens with the values of the properties. First of all, we fix a constant temperature in the water of the thermostatic bath and wait for some minutes. Now we have, for example, a temperature of 19.5 degrees Celsius remaining constant in time, that is, steady state. Now we turn the wheel to set a certain volume, for example, 3 cubic centimeters. It can be seen that the manometer shows a value of 14.75 bar of pressure. This value corresponds to the behavior of the fluid when we have chosen given values of temperature and pressure. Keeping a constant temperature value, we turn the wheel in order to obtain a new volume value, for example, 2.9 cubic centimeters. Looking at the manometer, we can see that pressure has been modified to 15.0 bar as a result of the fluid behavior. If the temperature value is modified to 22 degrees Celsius and the same value of 3 cubic centimeters is selected, as in the previous experience, a new pressure value is reached, corresponding to 15.0 bar, different than the one of the first experience. Experimental evidence indicates that the resulting value of pressure in the fluid depends on the previously fixed values of temperature and volume. It can be said that, from the 3 controllable and measurable properties in the apparatus, only 2 can be fixed in an independent way. This suggests a mathematical dependence that can be expressed as follows. Pressure depends on temperature and volume values. In physical terms, we can say that, as a pure substance, the fluid only has 2 degrees of freedom in its properties. If the explicit variable pressure is moved to the second term of the equation, we will obtain as a result that there is actually a function in the fluid relating the 3 properties in the shape of a homogeneous equation. This equation that describes the thermal behavior of the fluid is known as the thermal equation of a state. If we had fixed temperature and pressure instead of temperature and volume, we could observe the resulting evolution in volume. In the same way, if we had chosen pressure and volume as independent properties, we could observe the evolution of temperature. In any case, we obtain different mathematical relations of the same physical dependence. PVT diagram, initial measurements at constant temperature. Now we are to obtain a table and a graphical representation of a set of PVT values of sulfur hexafluoride in the range of measurements in which our device is able to work. We know that from the 3 properties, pressure, volume, and temperature, only 2 of them are independent in order to be used as control properties. We choose 2 of them to control our experiment, temperature and volume. We start the experiment by fixing a temperature value of 19.5 degrees Celsius. The volume is fixed to 4 cubic centimeters. Then we note the resulting value of pressure, 11.50 bar. All the obtained data will be gathered in a table and represented in a plane diagram, being volume the property of the x-axis and pressure the property of the y-axis. Maintaining a constant temperature in the value of 19.5 degrees Celsius, we are to reduce the volume in fixed intervals of 0.1 cubic centimeters, writing down the value of pressure in bar. When reducing volume at regular intervals, a progressive increase in pressure is observed. That is coherent with everyday experiences, such is the case of air. When reducing its volume at constant temperature, its pressure increases, and when increasing pressure at constant temperature, its volume decreases. This behavior is repeated in a similar way until, at a given time, a new reduction in volume at constant temperature doesn't lead to the corresponding pressure increase. What has happened in the perceptible behavior of the fluid? Let's take a look at the fluid. Until the previous moment, a single homogeneous and transparent phase of the liquid was observed. But now, a thin layer covering the surface of the mercury plunger is observed, showing the existence of a separation interface between the lower and upper phases. This observation evokes a question: what has happened? First, appreciation. Pressure in the manometer is higher than the atmospheric pressure of the water surrounding the tube, and this pressure remains steady in time. This means that the tube containing the fluid remains leak-tight, preventing any fluid to enter or exit the system. Then, the system is closed. Second, appreciation. The only thing that could have happened is that any transformation in the state of the fluid has taken place. The fluid has split it in 2 different phases that can be differentiated due to the different refraction that light suffers when crossing the sample. We know that light refracts in a different way in substances with different density. This suggests that both phases may have different density values. On the other hand, gravitational pull orders materials in a way that the denser are located at the bottom, whereas the low dense ones are at the top. Moreover, there exists an intimate contact between both phases, what allows molecules to pass from one phase to the other. Thus, we can formulate the following hypothesis. Initially, the fluid was in gas state. When reaching a determined value of pressure and temperature, a small additional reduction in volume does not produce an increase in pressure, but a molecular aggregation from gas phase to liquid phase. Pressure and temperature remain constant with a reduction in the value of volume. PVT diagram. Initial measurements at constant temperature. We will contrast the exposed hypothesis in the following experimental measurements. We continue with the volume reduction at constant intervals of 0.1 cubic centimeters. We notice that the total volume of the fluid is reduced. An increase in the quantity of fluid in liquid phase in relation with the total volume is observed, whereas the gas fraction is reduced. Pressure remains constant during the phase change, as well as the temperature. At a certain moment, the liquid fraction fills almost the whole available volume, while the gas fraction is already small. What will happen if we continue reducing the volume? When reducing the total volume, the condensation of the last gas bubble takes place. Then, the liquid occupies all the volume. What will happen now if we continue reducing the volume? A further reduction of the volume needs more effort in order to turn the wheel. We observe that the volume is barely reduced, while pressure rapidly increases. We can observe that the liquid bears high pressure values without a perceptible change in volume. In fact, the safety limit in pressure is easily achieved. What will happen if volume is rapidly increased? When doing so, we can see an abrupt formation of gas bubbles in the heart of the liquid. We are observing the boiling or vaporization of the liquid at constant pressure and temperature. The description of the first PVT data. Now we have available a complete set of measurements at constant temperature. In the table of results, three kinds of behaviors can be identified, following the stated hypothesis. Initially, the fluid is supposed to be a gas. Volume reductions generate a slow increase in pressure at almost regular intervals. In a certain moment, what we suppose to be the first condensed liquid drops appears in the heart of the gas. At constant temperature, the total volume is reduced, remaining the pressure constant. By continuing with the reduction of the total volume, more and more quantity of condensed liquid appears, as the quantity of gas is reduced. During this process, pressure remains constant. In a certain moment, the last gas bubble disappears in order to lead out to a single phase of liquid. From now on, when we try to reduce the volume, an increase in pressure is observed, being this increase rapid and quick. If we represent graphically this information, we can see the following. The gas region, in which the fluid suffers a smooth increase in pressure as the volume is reduced at constant temperature. This region is called the superheated vapor region. The appearance of the first drop of condensed liquid. We can state that the gas, at this pressure and temperature, has saturated its capacity of maintaining all its molecules in gas state, grouping because of this some molecules in the first liquid drop. We denote this state as saturated vapor or saturated gas state. A region in which the total volume is reduced, while pressure remains constant and both liquid and gas phases coexist. A gradual reduction in volume produces an increase in the proportion of the liquid with respect to that of the gas. We can denominate this equilibrium region as liquid-gas region. The disappearance of the last gas bubble, resulting in a unique liquid phase. In this border state, we can say that the liquid, at this pressure and temperature, has saturated its capacity of maintaining all its molecules in liquid state, grouping some of them in the first gas bubble. We call this state saturated liquid. The liquid region, in which the fluid experiments an abrupt increase in pressure as volume is reduced at constant temperature. We denote this region as the compressed liquid or subcooled liquid region. We don't know the mass of sulfur hexafluoride present in the experiment. What we know is that this mass is always the same because the system is closed. Hence, we can draw in parallel with the volume axis a new axis of volume per unit of mass, that is to say, specific volume, with units of cubic centimeters per gram. This specific volume property is the opposite of the density, expressed in grams per cubic centimeter. This axis will increase in the opposite way as the volume axis does. Thus, we can reinterpret the results in terms of density. The following can be observed. The gas region, in which the fluid suffers a smooth increase in pressure as the density is increased at constant temperature. This region is called the superheated vapor region. The appearance of the first drop of condensed liquid. We can state that the gas at this pressure and temperature has saturated its capacity of maintaining all its molecules in gas state, grouping some molecules in the first liquid drop. We denote this state as saturated vapor or saturated gas state, which represents the density of the corresponding saturated vapor. A region in which the total density is increased, whereas pressure remains constant, and both liquid and gas phases coexist. The increase in the proportion of liquid with respect to that of the gas is translated into an increase of the total density. We can denominate this equilibrium region as liquid-gas region. The disappearance of the last gas bubble, resulting in a unique liquid phase. In this border state, we can say that the liquid, at this pressure and temperature, has saturated its capacity of maintaining all its molecules in liquid state, grouping some of them in the first gas bubble. We call this state saturated liquid, which represents the density of the corresponding saturated liquid. The liquid region, in which the fluid experiments an abrupt increase in pressure as density is slightly increased at constant temperature. We denote this region as the compressed liquid or subcooled liquid region. The set of PVT data. What will happen if we repeat the measurements at a higher temperature? For a different temperature and a given volume, will the same values of pressure be obtained, or will these values be different? Will the states of saturated liquid and vapor take place in the same values of pressure and temperature? We repeat the experience now, maintaining a constant temperature of 22 Celsius degrees. We are to reduce the volume once again in the same fixed intervals of 0.1 cubic centimeters, writing down the pressure value in bars. At first, we observe that, for the same volume or density value, pressure values in the gas are higher than the ones of the preceding experiment. It seems that the increase in temperature is in correspondence with a behavior of the gas at higher pressure values. When reducing gradually the volume, increase in density, pressure increases slightly, reproducing the aforementioned behavior, typical of the gas phase. At higher temperature, the phenomenon takes place at higher pressure. In this new isotherm, will the appearance of the first liquid drop take place at the same pressure and volume conditions? The fluid demonstrates that this is not the case. The state of saturated vapor takes place at higher pressure and lower volume values when temperature is increased. Once the first drop of condensed liquid is obtained, a further reduction in volume or increase in density takes place at constant temperature and pressure, as happened in the first experiment, although the values of these properties are higher. In this new isotherm, does the disappearance of the last gas bubble happen at the same pressure and volume conditions? Once again, the fluid demonstrates that this is not the case. The state of the saturated liquid takes place at higher pressure and at a slightly lower volume or slightly higher density when temperature is increased. Lastly, with all the fluid in liquid state, trying to reduce the total volume produces a rough and quick increase in the pressure. The behavior of the fluid has been reproduced, but at higher temperatures, resulting pressure values have also been increased for the same value of volume. If we reproduce the experiment at several higher temperatures, 25.4, 32.0, 37.4, and 42.1 degrees Celsius, what happens? The answer is that the behavior follows the same pattern, but as temperature increases, resulting pressure values also increase for the same value of volume or density. On the right side of the PV diagram, we can see the sequence of saturated vapor states. These states of different volume, pressure, and temperature have in common that they are the states in which the first liquid drop appears in the heart of the gas. By means of an isoline, we can link these representative points. In the states in which we have not taken a measurement, this curve offers a prediction of its approximated situation. In the same way, in the left side, we can observe the different states of the saturated liquid. These states, of different volume, density, pressure and temperature, have in common that they are the states of the fluid in which the first gas bubble appears in the heart of the liquid. By means of an isoline, we can link these representative points. In the states in which we have not taken a measurement, this curve offers a prediction of its approximated situation. It seems that both the two lines, saturated liquid and vapor, tend to join in a unique point as pressure and temperature increase. Can we observe this experimentally? The critical point of a substance. To observe what happens with the evolution of saturated liquid and vapor lines, we are to perform a measurement at 45.5 degrees Celsius, following the same procedure as for the previous isotherms. The initial behavior of the pressure in the gas when volume is reduced is similar to that of the previous isotherms. Slight increase in pressure when volume is reduced. As in previous experiments, we could expect that, in the way that volume is reduced and pressure is increased, at a certain moment the first liquid drop would appear. However, this phenomenon does not take place. As the experiment goes on, a different behavior is observed in the pressure when reducing volume. Instead of a slightly increase, which is a characteristic of the gas behavior, a rough increase in pressure takes place, a characteristic of the liquid state. When we reach small volume values, we can observe the rough increase in pressure, typical of the liquid state. When representing the PV curve, the existence of a turning point is noticed, with horizontal slope. No simultaneous coexistence of liquid and gas has been observed. Rather, a continuous transition from gas to liquid state, with a gradual increase in density, has been observed. Now we are to perform another isotherm measurement at 48 degrees Celsius. The experience is repeated by following the previous procedure. At no time the coexistence of the gas and the liquid is observed. Instead of this, a gradual transition from the gas state, less dense, to the liquid state, which is denser, is observed, with the corresponding behavior of pressure. No horizontal slope point is noticed in this isotherm. With this, it seems that the point with the horizontal slope of the 45.5 degrees Celsius isotherm is the limit of what, at lower temperatures, was a transition segment from saturated vapor to saturated liquid at constant pressure and temperatures. We could say that this upper point of the liquid vapor region is saturated vapor and saturated liquid at the same time. This uniqueness in the state of the fluid is named critical point of the substance. In the case of sulfur hexafluoride, it takes place at 37.5 bar and 45.5 degrees Celsius. The critical point is a fixed point for the substance. No matter how many times the experiment is reproduced, in any direction of pressure, volume and temperature variation, it always takes place at the same values of pressure, temperature and volume. This critical point means an upper limit of pressure and temperature in which the coexistence of gas and liquid takes place. Over these pressure and temperature values of the critical point, the transition from gas to liquid, or vice versa, takes place within a gradual variation of density in the fluid, with no observation of the coexistence of the gas and liquid states. In the same way, the discontinuity between the two phases has no place.